Hi, I'm Meredith, and I'll be talking about magnetically actuated satellites. Magnetically actuated satellites use magnetic coils that torque against Earth's magnetic field. The torque produced is restricted to the plane perpendicular to the magnetic field, which varies over time as the satellite orbits. I considered three sets of satellite dynamics. First, a purely magnetically actuated satellite, shown on the left, a magnetically actuated satellite with a reaction wheel that allows arbitrary torque about the z-axis, shown in the center, and a fully actuated satellite, shown on the right. I used ILQR and Drake to optimize trajectories for all three systems, aligning a camera vector, shown in red, with an imaging target, shown in green. The optimization was unconstrained except for implicit constraints posed by the satellite dynamics. Next, I used two sets of sums of squares optimizations in Drake to find an angle phi such that if the satellite is pointed within phi degrees of the trajectory state at time step I, there is guaranteed to be less than 5 degrees of pointing error at the end of the trajectory. On the left of this slide, I've plotted phi over the duration of the trajectory. Then, we can see that phi naught is around 10 degrees for the fully actuated satellite, meaning up to 10 degrees of initial attitude error is guaranteed to converge to less than 5 degrees of attitude error by the end of the trajectory. However, the guarantee is much worse for the other two systems. Next, I empirically evaluated the stability guarantees by generating random initial conditions such that the initial pointing error is less than phi naught for all three systems, and then propagating the closed-loop system with LQR control. The set of angles phi is shown in red for reference. In practice, these trajectories show much better convergence than is guaranteed. This is in part because angular velocity error contributes to the value of the Lyapunov function at the end of the trajectory, so a state could be on the boundary of the goal set and still have quite low pointing error if the angular velocity error is high. Another factor is that certain initial conditions can lead to huge error blowup. For example, magnetically actuated satellites can't torque around the magnetic field axis, so an initial low spin around this axis is hard to cancel and can cause large divergence from the trajectory. As a result, guarantees for all initial conditions with the same value of the Lyapunov function are fundamentally very conservative, and performance with most initial conditions will be much better than is guaranteed. Another Monte Carlo simulation with random initial conditions such that the initial pointing error is 5 degrees for all systems shows large error blowup for the magnetorquer only system, relatively good convergence for the system with one reaction wheel, despite there being no convergence guarantees for the set of initial conditions, and near zero final pointing error for the fully actuated system. This again highlights the conservatism of the sums of squares guarantees and shows the power of additional actuators in improving stability. Thanks for watching!